This is a recording for AQA Discrete Mathematics, Graphs and Networks, section 4.1, where we're looking at planar graphs. Well, by a planar graph, we simply mean one which can be drawn without any edges crossing on a plane, or indeed a piece of paper, in other words. So we can, for example, look at K4, which is a complete graph with 4 vertices, which is sometimes drawn in this fashion. And has a crossing point here. However, we can redraw that to show that in fact K4 is indeed planar, and instead of the crossing point that we put in for the final connection, then we can go around the outside, and this is then the same graph. It's actually isomorphic to, and that will be discussed in another video. But what we have now is the plane is divided by these edges into regions. So we talk about the graph dividing the plane with vertices V, edges E, and regions R. Sometimes the regions are referred to as faces because these were also looked at in terms of polyhedra. So you may come across the idea that F is used for the regions as they're called faces. So a planar graph then is one which is possible to draw on the paper, on the plane, without any edges crossing. Another way of representing a graph is to give what's called an adjacency matrix. We can see here the matrix for the vertices A, B, C, D, E, and F. Now it's full of zeros and ones. A 0 indicates that there's no edge, and a 1, for example, in the first entry there, or the third entry rather, in the first row, indicates there's an edge going from A to C. Well, here's a GeoGebra file which is looking at the same matrix. So I've marked in here the leading diagonal because if we want to look at this, obviously if there's a line going from A to C, there must be one going from C to A. So it's symmetric in this leading diagonal. So from A to C has already been marked in. Reading along the top row, we also need one going from A to E. We can then move down to the second row and see that B has to be joined to D, E, and F. The third row says C to A, but we've got that. We can ignore everything below this leading diagonal and just look at the ones above. So we've got to go from C to E and from C to F. And then finally there's a edge going from D to E. So there's the complete graph for the adjacency matrix. Now we want to decide, is this a planar graph or not? Well, there is an algorithm that we'll look at which will decide this, but we'll look at that in another video. However, for our methods, just moving a point to see whether we can get rid of those crossings is sufficient. And you can see that we could move them in this fashion so that we now have exactly the same graph, or at least an isomorphic graph, but with no crossings. So there we are. We've shown that the graph given by this adjacency matrix can be drawn in this way, and therefore we can state that this is a planar graph. Now if we have a planar graph which is connected, as these are, then Euler came up with a formula which said that V plus R is equal to E plus 2, where V is the vertices, R is the regions, and E is the edges. Sometimes you'll see this written as V plus F minus E is equal to 2, where there we've got V is the vertices, F is the faces, and E is edges. For this particular one, we can see that V is equal to 4. R is actually equal to 4. Now you might at first sight think it's 3, 1, 2, 3, but there is a region outside of the graph itself. So there are 4 regions there, and edges is equal to 6 in this particular example. So you can see that we have that V plus R is equal to 4 plus 4, which is 8, and E plus 2 is 6 plus 2, which is also equal to 8. So Euler's formula works for this situation. We can consider the same formula for this graph that we drew, where we have this time that the vertices is equal to 6, the regions 1, 2, 3, 4 again, and the edges, if you count them, there are 8. So we have that V plus R is equal to 6 plus 4 is 10, and E plus 2 is 8 plus 2, which is also equal to 10. We've talked about the complete graph K4, which has got 4 vertices, each joined to every other one. K5 has got 5 vertices, and this then has a situation where we need to join every vertex to every other one. This is not quite finished, because you see that we need to join vertex C to E. Now we could try going directly across, but of course there will be a crossing point there. So let's go round from C to E. So that gives us 4 of our vertices having order 4, but we've got D, which has still got to be connected to A. And of course we can't go out from D to A, so we could try coming across directly, but there's going to be a crossing point. So whichever way we go, there must be a crossing. And therefore we can say that K5 is not planar. In fact, it must be clear then, if K5 isn't K6, K7, in fact the last one to be planar of the complete graph is K4. We can also think about complete bipartite graphs. Here we have K33, and we'll see it's partly redrawn here in a cyclic nature, but we need to also then join D to C. And again we have the same situation. We could try to go round, but we would then cross the arc going from E to B. So whichever way we try to do it, we must get at least one crossing point. So K33 is not planar. Now these two, K33 and K5, are critical in a theorem about planar graphs, which we'll look at in a later video. And that theorem is known as Kuratowski's theorem.